Hello guys, this is Basseret and I'm giving this recorded session for you on practice assignment 3 in the course of CSEN 704, which is following lecture 3, which is about spatial databases and R trees. First question and second question, as well as third question in this practice assignment is following. Write a spatial query in PostGIS for the statements. These are the statements as follows. First, get all the buildings in the Quad-Sula region. Second, show a list of all the names of regions adjoining the Hokkaido region. List all regions that are 100 kilometers away from Hokkaido. This is the third. So for each one of those, we wanna write or type down a spatial query, something which would be similar to regular relational database queries. So what is PostGIS? Let's just recap what was PostGIS in lecture 3. Well, PostGIS is a plugin for PostgreSQL, an open source software, a plugin for the PostgreSQL to implement or to design a spatial databases. And it has the following geometric data types, such as point, line string, polygon, geometry collection, as well as spatial functions. Spatial functions such as st-intersects. So as we see here in the figure, we have A and B and they intersect. Other spatial functions like contains or within and touches. Two others, crosses and distance within, D within. Other spatial data functions here would be ANDing, and it works as follows. These just are few examples. Finally, following spatial data functions, we have also something like st length of geometry, which would return a float corresponding to the length of such geometric object. st area geometry. So if we have a geometry of an object, the area here would be returned as a float, and that would correspond to the area. Then we have as text. If you got a geometry, so that would be returned as text. It's useful in that type of queries where you would get or you would like to have the geometry as part of your outcome. And finally, geometry from text, which would return geometry based on your text. So let's getting started with actually solving the first exercise. Get all the buildings in the Quad-Sula region. So Quad-Sula region is somewhere, someplace specifically, and we want to retrieve all of the buildings in this region. So all of the buildings within this region. How would such query look like? As follows. We select a.id, a.name, st as text, a.thegeometry, all of that, okay, recognize that as point, or actually name that as point. That would be from what? From two collections or from two tables here would be building and region. Building A, so actually the ID corresponds to the ID of the building, the name is the name of the building, and here the geometry is the geometry of the building, and all that would be recognized as, or actually be named as a point. Where then within the geometry of that building to be within the geometry of the region. And that region would be Quad-Sula as required, or as actually. Second one, show a list of all the names of regions adjoining the Hokkaido region. So what is the meaning of the word adjoining here? Well, the list of all names of regions that would touch the Hokkaido region. Okay, actually the neighbors of that Hokkaido region. So we can use actually the function of touch. So here we go. Select p.name, where p will correspond to the region from the table region and another table region. You've got the region A and the region B. We're retrieving the regions B, and those regions B where b.geometry touches the geometry of A, where A then would be Hokkaido region. Exercise number 3. List all the regions that are 100 kilometers away from Hokkaido. How would we do this? Similar to the ones before. In this case, which function would we use? Possibly t within. Third exercise, list all of the regions that are 100 kilometers away from the Hokkaido. So similar to the one before, indeed, but what would be the function here? Something that would be related to distance. It is distance. So in this case, we would be retrieving where the distance of A.geometry and B.geometry less than or equal to 100. So how would this go? You select the GID, okay, the geometry ID could be, and name, okay, and the geometry of the B, and where B would be a region, something or some entry, some row from the table region. And on the other hand, you've got region A, where region A would correspond to the Hokkaido. And we would be looking for those regions where they would be of distance less than or equal to 100. And of course, we just say b.name is not Hokkaido, so actually we are not just comparing the same thing. All right. Now we're done with this first part of the SQL queries which are related to PostGIS. Here we got R trees. So similar to what we had with the B trees, as we understood from the lecture, here for spatial data, we will be using something such as R trees. In this exercise, we want to construct an R tree index for the following data points. Each region contains at most 4 data points and at least 2 data points. So intuitively, actually, looking by eyes on this, we can see that simply some stuff like those could be bounded easily, and seems fair to just have them grouped this way, right? What about this one? Actually, we can do something like that. Would this work? Not really. Why? Because here we would get one region, such as this one, with just one data point, and that's not satisfied according to our design, which would make each region contains at most 4 data points and at least 2 data points. So just undo our group, and then we would have these all put together, right? Okay, so we go then. And we find these points in our data. How would they get grouped? As we said, we will group them as follows, because that which makes sense at this point. Okay. And then these would be technically our nodes, our leaf nodes. So we've got 4 now. How would those 4 be pointed to? By one root node, and that would correspond to the R right there. Then we convert that to an actual tree with nodes, inner nodes, and leaves. How would that look like? Exactly like that. So we can see here actually, we've got the R, our root, which corresponds to this one. Then that points to A, that group. Second pointer to B, that group. Then second pointer points, the third pointer points to C, that group, and so on. And now let's go further and with question number 5. We would like to modify the R tree constructed in question 4 after inserting a new data point, which is 15, where it would be placed right there. So how would our R tree look like after the insertion of such data point? Would it be any different? Well, we can remember that once we had our original R tree, it had the following regions, right? Something like that. Something that points 1, 2, 5, 6 together, 14, 9, 8 grouped together, 11, 12, 13 together, and those 4 down there together, right? What about 15 then? Where would it be placed? Well, seems fair to have it along that group. Would there be enough space? Yes, there would be. And we can see basically that, well, yes, and there is enough space to fit 15 as well. So basically that would be added and it would be part of the D branch right there. Easy. And with exercise number 6, another insertion of another data point, which is 16, which we can see right there. Well, would the tree then stay as we had it in exercise number 5 and exercise number 4, or will it need to be changed? We'll see. Well, how was our regions before? Well, we had those group put together. We had those group put together, and those along actually the new 15 from the exercise, the previous one, and we have got those 4 put together. But now this point 16 have just been added. Which group would it belong to? Well, it seems fair if we would add this 16 to be part of which group? This one, right? So all of this would be one group. However, then remember, as we have seen before, we can have at most 4 data points by design and at least 2 data points. We've got now in this group, how many points? 5 points, which doesn't make sense then, or actually doesn't matches our design. So how could we fix that? Basically, we would split that group into 2. It makes sense that those would be the 2 new groups, right? Then what? Those would be our leaf nodes. Then we go up one level, and as we had our previous tree, how did it look like? We had then actually our root directly, and our root was something as follows, right? Is there any problem now? Well, there is, which is that, well, a node can have at most 4 data points, such as actually we had with our P plus trees. In this case, actually, we are working in a very similar manner. We have, or we can have actually at most 4 data points. But then here we've got 4, no, we've got 5. Here is 1, here's the second, here's the third, fourth, fifth. So probably now we want to create another node on this level to split those 5 into these 2. How would that look like? Let's see. Well, we've got our leaf nodes, A, B, C, D, E, like we said. Then those could be actually our previous level of nodes. If we go up, we've got to get 2 nodes here, not just 1, as we said. So those would be G and F. Then what? We go further one step, and we have now our root of the tree, grabbing up all of those together. And hence, we can just build our tree as we have seen with the previous examples right there following the diagram. So we've got R points to F, and G, those big regions, the internal nodes actually here grouped in blue. Then we've got those pointing to F, pointing to A and B, and G pointing to C, D, and the E. All good? Let's go further. Modify the tree constructed in question 6 after the deletion of point 2. Okay, so here we go. This was our construction solving question number 6. And now this point 2 would be deleted. This 2 would be removed. How would our tree finally look like then? Well, this is our tree. We've got the 2 here, and here is just another illustration of the tree using our minimum bounding boxes. How would our tree be any different after the deletion of 2? Well, we deleted 2. Would we need to make any adjustments? Not really. We have actually enough amount in A for it to stay alive. You got 3 and can stay actually as long as it has a minimum of 2. So that's totally fine. Then accordingly, we'd have our 3. We just removed the 2. All good. Exercise number 8. Modify then the tree constructed in question 7 after the deleting of another point, which is 3. We've got this 3 right there. Okay, and we want to delete it. How would this then look like? Right there, we've got the 3. If we just remove it, Would that cause any problem? We would need any adjustments? No, we wouldn't. But we can actually just adjust the box, the minimum bounding box right there for optimization of our tree. And accordingly, 3 would just be lost right there. You've got the original tree, and accordingly, just remove 3. You've got the same node as is without the 3. Going further, the R tree we have just constructed in question 8. We want now to delete point 4. Once we delete that, what would happen? Would we need any sort of adjustments? Let's see. Here we've got the 4. Once we delete this 4, do you remember what just happened? We had our tree as is, actually, in the other cases. This time, we will have a problem. Remember, from the very beginning, we said that by design, our tree would have per node at most 4 data points and at least 2 data points. And now, once we got the 4 removed, we would have a problem with this minimum bounding box, with this MBR. So we would need some form of adjustments, which could be that, well, let's put all of those back together, 7, 10, and 16. Right? We had those, and then we've got to break these 2 regions and put those back right there. Makes sense. All good. Then what? Just have the root right there, and that would be R. How would then the adjustments look like in our tree diagram? Well, easy. F and G has been deleted. Why? Because, well, you've got a B, and we removed the 4 from there. So we got only 1 point there, and that doesn't work. So what will we do about this? We delete the B, and then we've got a problem with F. What will we do with that? Well, we delete also the F, we delete the G, and then the 4 would be merging with the closest region to it, which then would be, or could be then, E. So E would have 7 as well. Very good. Finally, the last part of this practice assignment, exercise number 10, which is on geohashes. The exercise goes as follows. The following geohashes are associated with the following regions, where 9V corresponding to Cairo, 8V corresponding to Giza, and 7V would correspond to New Cairo. Given the geohashes above, those 3 provide the geohash of the regions below. If the region is within any of the 3 regions above, append hyphen -X, where X is the first letter of the region name. So we will be given few regions, and we'd like to append those accordingly to these 3 regions if they belong to. Well, let's just quickly recap what was that all about. Geocoding. So geocoding works in this manner. You've got, for example, in this figure, a geohash of the world. We've got the map of the world, and we have actually kind of indices or encodings pointing to the different parts. So let's zoom in and dig to part of 9. Well, then we go 1 level down, and this we got to part of USA. We go 1 more level down, 9V now. So we've got 2 levels down here, and we've got 9V corresponding to a more specific part of the United States. We go 1 more level down, And we've got that. Well, now we have 9VB, 9V8, 9V2. We can select and so on. So actually, we are going more specific into that part of the world. So you got the idea. Let's go back actually to our problem. So for the first and second regions, تجمع الخامس and Heliopolis, تجمع الخامس would belong to what? New Cairo. So then we would append the first letter of تجمع الخامس to the encoding of New Cairo, which then would make 7V-T. What about Heliopolis? Heliopolis belongs to Cairo. So then that would be 9V dash the first letter of Heliopolis, which is H. What about Muhandisin and Rihab? For Muhandisin, then we would have 8V, which belongs to Giza, where Muhandisin is part of Giza, so 8V-M, and Rihab would be part of New Cairo. Accordingly, that would be 7V-E. And for the last two, Doki and Maadi, for the Doki belongs to Giza, so then we would have 8V-D, and for Maadi, that would be 9V-M, where Maadi is part of Cairo. And that was basically it for our practice assignment and accordingly for the tutorial sessions 3. Hope you got it.